We'll just start in 2 minutes. Let me set up. I'm setting it up. Okay. Is my screen visible? Anybody can see?
No, sir. No, now it's visible, sir.
Great, great. Okay. Okay, so very good afternoon, everyone. So welcome again. So due to some unavoidable reasons, I had to shift this session, like prepone this session to like for today. So otherwise, we normally meet on Sundays, 3 to 5. So recording has started. Yes. So this is our last session today, and what you have discussed in the last week, you have discussed lead and lag compensators. Very simple questions. You have not gone into the design. Oh, sorry, it's week number 12. So you have not gone into the design details. So basically, you have only gone through what is a lead compensator, what does this lead compensator do, and what is a lag compensator, what's its effect, why do we use them. That's what you have done in your lectures. But how this lead and lag compensators actually work and how you design them, that's not a part of this course. Okay. So when is your exam date?
25
Can you
October,
confirm?
25th of October.
Only one shift?
Yes, sir. I think so because I'm in two courses. I don't know. Maybe two sets.
Okay, no problem. So let me start. So we will start with lag compensator. So lag compensator. So and what does this lag compensator do? You have learned it improves the transient response. It improves the transient response. Sorry, it improves the steady state response. So it's lag. How does it do? I'll show you. Right. So basically, whenever you want to achieve some desired goal for your system, and it's not always possible to manipulate your system, so you have to add something additional to that system to achieve that goal, right? For example, you have for example a plant which is g of s, and it is not giving you what you actually desire for, right? So then what you do, right? So for example, yeah, there is this controller k. This is your plant. There is negative feedback, right? So there is some output. Why? Now, so let's see, what is the open loop transfer function of this plant? It is k g of s, which we can write k g of s is a uh, g of s is a transfer function. It has some zeros, it has some poles. So we can write it like this: s plus z1 into s plus z2, so on up to s plus zn, divided by some poles p1, p2, so on up to pn, right? So this is actually transfer. This is basically we have considered a zero order. Sorry, we have considered a first order transfer function type zero. There is no pole at the origin. Sorry, it's type zero, so there is no. It's not first order. It's nth order. So, but there is type zero, right? There is no pole at the origin. Now, what I want to do for a type zero system, if I apply unit step, what will be the steady state error? What will be my steady state error? So ESS will be given by 1 divided by 1 plus Kp, right? 1 plus Kp. So I said what I said in the beginning, this lag compensator, it improves the steady state response. It means it somehow, if it improves this response, it means it decreases the steady state error. Error should decrease. That's what. So see, when we talk of the properties, the improvement in steady state error, the steady state response, that means steady state error is as small as possible. If I am saying my lag compensator improves my steady state response, it means my steady state error is as small as possible. The tracking is perfect. So this means my ESS is less. So how will we make this ESS less? By increasing this term, right? So somehow we increase this KP, right? So we increase this gain. So that's what we take into consideration these compensators. So this is a lag compensator. Normally, a lag compensator, this transfer function is given by, I'll write the transfer function. So for example, G lag transfer function, you all know the transfer function is 1 plus ST1 divided by 1 plus alpha ST2, right? So here, this alpha is greater than 1. It means my pole is near to origin. And okay, yeah. So pole zero pole, you have learned everything. So I'm just recalling it. Similarly, for a for a lead compensator, your zero lies near to origin. So now let's start directly from the questions. No need to just revise it. So let's start from your assignment questions. Now there is this question. So you have covered, I assume, so I'm not going into the details now. I assume you have covered everything in your lecture. So I'm directly starting questions. So the question is a lead compensator. We have similar question in your assignment. A lead compensator. So when I'm saying lead compensator, its transfer function should come into your mind. Introduces a lead compensator introduces an open loop 0 at -2 and an open loop pole at -5. Then find the corner frequencies. Find the corner frequencies of the compensator's transfer function. See, very simple. Let's look at the question. The question is saying, so we have a compensator which introduces, let's assume, okay, the transfer function of the compensator is GC. So the question is saying the compensator, it introduces an open loop 0 at -2. So can I write it S plus 2 and an open loop pole at 5? So can I write it S plus 5? Very simple. Now, when we have to find the corner frequencies, we always write this in terms of time constant form. So we will write this in time constant form. It will be GC is equal to 2 into 1 plus S by 2 divided by 5 into 1 plus S by 5. This, whatever is down S, this is your corner frequency. So the corner frequencies are, 2 and 5. Okay, so this is the gain here. So 2 and 5, the terms which are there with the S, so you know that very well because we have done this in detail. Now the next question is for the same transfer function. So we have now got this lead compensator. So we have got its transfer function. We have got its transfer function. Now the question is, if it is a lead compensator, find the maximum lead in degrees. Find the maximum lead in degrees. Right? Provided by this compensator. Provided by this compensator. Right? Your options are 45, Option B, 41.8. Option C, 30. And option D is 25.4. Please try to solve it. Please try to solve it. This is, you have to find the maximum lead. There is a direct formula as well for this question. But yeah, you try to solve it. I've given you options as well. First, if we write this transfer function, GC, we have 2 by 5, or directly, we'll write S plus 2 divided by S plus 5. So I will write the sinusoidal transfer function that will be j omega plus 2 divided by j omega plus 5. And if I have to find the angle of GC, what will be the angle? Angle will be tan inverse of omega by 2 minus tan inverse of omega by 5. Okay. What now, how, when will this angle be maximum? So because this is the angle provided by the lead compensator. So when will this angle be maximum? It will be maximum at when the frequency. So what is the frequency um, for which this angle is maximum? Right? So that frequency omega m for which the lead is maximum is given by geometric mean of the this corner frequencies, geometric mean of corner frequencies. So what is this? What is omega m then? Omega m is, what are my corner frequencies? 2 and 5. It's 2 into 5 is equal to 10. Okay. So omega m, I got 10. So it means my angle C is max at omega equal to omega m. So then what is my angle GC? Tan inverse of omega m by 2 minus tan inverse of omega m by 5. You solve it and tell me omega m is root 10. So it will be tan inverse of root 10 by 2 minus tan inverse of root 10 by 5. Tell me the answer. It should match with the options. Tell me which option is correct. 26.3, Marvin. Can you check? That's no option. 26.3 is no option. How did you solve it? So let me solve it. Tan inverse of under root 10 over 2 minus tan inverse of under root 10 over 5. 25.37. So this should be the correct answer. Did everybody got this? 25.37. This should be the answer. So the maximum phase lead. Okay, good. Now, another type of question that you face in these lead lag compensators is that for the same problem, if you are asked the frequency at which the maximum phase lead, lead would be provided is would be provided is this is the question from your assignment. So now if you have to find the frequency at which this maximum phase lead would be obtained, that frequency is directly calculated. We have calculated, you see here. So this frequency, we denote it as omega 1. It's calculated as geometric mean of the corner frequencies. So here we have two corner frequencies. It will be 5 into 2. So it will be root 10. It will be 3.16. Okay, so sometimes you're asked such questions as well. Fine. So one more question. Good question. I would expect I would expect all of you to solve this question. So in problem 2, the problem 2 is we have the transfer function s plus 2 of a lead compensator divided by s plus 5. So in problem 2, it is desired that the low frequency magnitude frequency magnitude value in decibels. So remember, it's in decibels of the compensators sinusoidal transfer function. So it's desired that the low frequency magnitude in decibels of the compensator sinusoidal transfer function be 20 decibels. Then the value of the parameter Kc. Then the value of the parameter Kc is. What is Kc? I'll tell you. See, it's a good question. So we had this transfer function Gc, which is s plus 2 divided by s plus 5. The question is saying there is some gain as well, which is Kc into s plus 2 divided by s plus 5. Find this Kc if the initial magnitude is 20 dB. If the initial magnitude is 20 dB. The initial magnitude is 20 dB. Very good. First, see what is the type for this system. There is no pole at the origin. So things are given in decibels. There is no pole at the origin. It's a type 0 system. Now see. You remember that formula, initial magnitude formula, which we used to apply in Bode plots, right? Initial magnitude is minus 20 if there is a pole at origin into r log of something at the initial frequency plus 20 log k is equal to initial magnitude. But here there is no pole or 0 at the origin, so that term will vanish. So the formula will be 20 log of k. 20 log of Kc is equal to 20, right? Very simple. So initial magnitude is given 20 decibels. That's why I wrote 20 log, because it's in decibels, 20 decibels. But what is Kc? In this case, the transfer function should be in time constant form, but the transfer function is not in time constant form. So first we will make this transfer function in time constant form. So writing Gc in time constant form, we have written it will be 2 by 5, 1 plus s by 2 divided by 1 plus s by 5. Okay, and here will be Kc. So what is my net gain? When I wrote the transfer function in time constant form, I got Kc 2 Kc by 5. It implies my 20 log 2 Kc by 5 is equal to 20. This and this goes. it means 10 is equal to 2 kc over 5. 5 goes, it implies kc is equal to 25. Did everybody understood this question? So I got my kc equal to 25. Okay. If there is any question, I can just okay, I will again explain this. I'll again explain this question. Just give me a moment. Okay. Yes, Marwan had solved it. So basically, you are given that initial magnitude of this lead compensator. So it's desired that the low frequency magnitude value in decibels is 20 dB, and we have to find the parameter value kc. The only trick in this question is you have to make sure that your transfer function is in time constant form. Then and only you can apply this formula, right? Because you remember whenever we were drawing Bode plot, we first made sure the transfer function is in time constant form, identify the corner frequencies, then plot those corner frequencies and move on, right? So these are the types of questions basically that you have in your assignment. So similar type of questions you have. So now let's solve one more question. There are actually many other ways. I will also show you. So I just showed you one way of solving these type of questions, like by solving this by finding the phase and then putting in the frequency where the phase would be maximum, and then getting the value of maximum phase. But there are direct formulas as well. So I believe there are some formula that maximum phase phi m, uh, sine of phi m is 1 minus alpha divided by 1 plus alpha something. So you just have to identify alpha. We'll do a question on that as well. But for the time being, let's do another question. The same way we did this question, we did it before. So we have a compensator. You're not okay. You're given a compensator GC. You yourself have to identify 5 into 1 plus 0.3 into S divided by 1 plus 0.1 into S. Okay. So what is the question? The question is, this compensator would provide a maximum phase shift off. This compensator would provide a maximum phase shift off. I'll give you options and I would encourage you to solve it. 20 degrees. Option B, 30 degrees. Option C, 45 degrees. Option D, 60 degrees. Okay, I'm giving you, make sure. So first, what do? You can solve it in many ways, right? You can just directly calculate alpha and then use the formula sine of phi equal to 1 minus alpha or 1 plus alpha, or you can directly find the angle. You can find the angle of this transfer function, of this compensator transfer function, and then you can put in when that angle will be maximum. That angle will be maximum when phi omega m is maximum, right? So we'll find omega m, right? We'll find the frequency at which the lead is maximum. So that is given by the geometric mean. So we'll find omega and then we'll put the value of omega, just evaluate tan inverse of that, and you'll get the answer, right? So you just have to remember one formula. B is what? 30 degrees. Yes, 30 degrees is the correct answer. So very good. So anybody else got 30 degrees? Marwan got it right. So these type of questions you have in your assignment. So there are many ways. So how did you solve it, Marwan? Can you explain? Okay, now let me solve it. Um, Omega is 5.77. Okay. Yes. No, I don't think so. Let me try. 10 over 10 over root 3. Yeah, 5.77. Very good. So okay. Let's solve it. Let's solve it. For the sake of completeness, let me solve it. So my first task is to find corner frequencies. And what are corner frequencies? Omega 1 by 0.3, omega 2, 1 by 0.1 directly. You can write frequencies because it is in um, time constant form, right? So this is actually T. This 0.3 is T. So omega is 1 by T. So you got it. Quantum frequencies. Now, what is the like the maximum phase lead will occur at frequency omega m, which is given by under root of omega 1, omega 2, and which you will calculate 1 by zero point 0.3 into 1 by zero point 0.1. It implies my omega m will be 10 over root 3. Okay, so then my phi m, which is the maximum phase lead provided by this compensator, it is tan inverse of 0.3 into omega m minus tan inverse of 0.1 into omega m, right? So, which is basically equal to tan inverse of root 3 minus tan inverse of 1 by root 3, which is equal to 30 degrees. Very simple. Right now, let's do a very good question. I'll give you options, so you will solve this. The question is the transfer function of a position servo system. The transfer function of a position servo system. These type of questions you might encounter in your gate, in your NSEM, no, your this NPTEL exam. That would be a bit easier, but okay, still. So the transfer function of a position servo system is given as GS. Transfer servo system is given as G of S is equal to 1 divided by S into S plus 1. This is the transfer function you are given, and a first order compensator is designed. A first order compensator is designed. Okay. So in a unity feedback configuration, there are many things in this question, so pay attention. In a unity feedback configuration, okay, so that the poles of the compensated system, so that the poles of the compensated system are placed at -1 plus minus j and -4. Find the transfer function of the compensated system. Find the transfer function of the compensated system. So now let's examine. So initially you are given a plant, the transfer function of which is given as 1 divided by s into s plus 2. Sorry, s plus 1. Okay, so this is the transfer function which is given. And then a compensator is designed in a unity feedback configuration. So we will make a compensator right now so that the poles of the compensated system, see, this is GS, this is GS, and a compensator is always connected in forward path. So a compensator I'll connect here. So GC of S. So initially, when there was only GS, the transfer function was this. But now, when we have a compensated transfer function, and that too in unity feedback, then what happens? This is my output C of S. This is my input R of S. So then the compensated system, then this whole compensated system, it has poles at -1 plus J plus minus J. It has this compensator, it actually, this whole compensated system then has poles at -1 plus minus J and -4. And we have to find the transfer function of a compensator system. So these type of questions are very, very good actually. So try to solve it. I will give you options. Option number 1 is s plus 3 divided by 2s plus 3. Option B. So you basically know how this transfer function normally look like. So you can assume any general transfer function. I'll give you a hint. This is B option. C option is 5s plus 1.6 by s plus 5. D option is 3 into 2s plus 3 divided by s plus 4. So I will give you one hint. Take compensator transfer function GC of s is equal to k some gain plus some 0 z1 and some pole p1. So basically we need to find the value of this p1 and z1. So you just plug this GCS here, then find the characteristic equation, because characteristic equation, the poles are actually, we can find them from the characteristic equation. So just find characteristic equation, just find the poles of the characteristic equation, or find a general form of characteristic equation. We can also find the characteristic equation from these poles, and then we can compare and we can get the values of Z1, P1, and K, and eventually we will get the transfer function of the compensator system. It's a very good question. It's a general question. It is not directly linked to compensators. It can be asked in general from your second chapter, second order systems, or when we learn closed loop systems, right? So basically you have to understand where this compensator is added. So it's always added in the forward path, right? So before the plant, because it has to manipulate it, it has to compensate it, right? So solve it and tell me what will be the characteristic equation. Let me solve it as well. So this is the compensator transfer function. So what will be the transfer function of the closed loop system? My net transfer function, which is CS over RS, will be equal to GC of S. I will write for you, you will solve it. GS, it's a negative feedback, 1 plus GC of S into GS. We can solve it. What is GC of S? K into 1 plus Z1 divided by 1 s plus p1 into my GSS open loop transfer function 1 into s plus 1 whole divided by 1 plus k into s plus z1. Somebody has solved it. You have basically solved the characteristic equation from the poles. Now find the characteristic equation from the transfer function. That you have solved it correctly. So from the poles, you have found the characteristic equation as s cubed plus 6s squared plus 10s plus 8. Now you find the transfer function from the transfer function, and then we'll compare the two, and we'll get the values for k, z1, and p1, and accordingly we'll get the transfer function. Yeah, very good, very good. Keep it up. And say 1 plus s plus p1 into 1 divided by s into s plus 1. Okay, so this will be k s plus z1 divided by s into s plus p1 into s plus 1 plus k into s plus z1. Okay, so if we solve it again, we'll get k into s plus z1 s cube plus p1 s square plus s square, or I'll write it direct, will be p1 plus 1 into s square plus p1 plus k into s plus k into z1. Okay, so we got the characteristic equation. So what's our characteristic equation from the transfer function is s cube plus p1 plus 1 into s square plus p1 plus k into s plus k into z1 is equal to 0. Now from the data, great. So somebody got the answer. What's the answer? Marwan found it. So P is 5. It should be P1. Yeah, P1 is 5. K is 5. And so is 8 by 5, 1.6. So option number C is correct. Option number C is correct. Very well done, Marwan. But let me complete it for others. So let me complete it for others. So from the data, what do we have? We have there are two poles, -1 plus minus j and -4. So we can form characteristic equation from this. So we can form it like this: s plus 1 whole square plus 1 into s plus 4. I did nothing. You just use these two poles. When you solve it, you'll get s cube plus 6s square plus 10s plus 8 equal to 0. Now you see you have this characteristic equation, you have this characteristic equation comparing coefficients. So P1 plus 1 is equal to 6. It implies my P1 is 5. P1 plus K is equal to 10. It implies my K is 10 minus 5 is 5. K into Z1 is equal to 8. It implies my Z1 is 8 by 5, which is equal to 1.6. Now let's write the transfer function. The transfer function is GC of S, K which is 5, into S plus Z, 1.6, divided by S plus P, S plus 5. And that's it. That's it. So these type of questions are very good questions actually, and you can expect in GATE these type of questions because uh, in lead lag compensator, there are not many questions which the examiner can ask. And that's why there is this possibility that you can mix up, that he can mix up. He can mix this concept with the concept of closed loop stability, feedback, etc., etc. Because design is not in your syllabus, right? So if design would have been in your syllabus, then we just start from here and then go on. That's a long topic. So one more question. Again, there are many ways to solve it. We will solve it differently now. The question is, you have a compensator GC of S whose transfer function is 1 plus 0.12S divided by 1 plus 0.04S. So you have this transfer function. It's a lead compensator. It's a lead compensator. It's a lead compensator. And we have to find the maximum phase shift. Find the maximum phase shift. Obviously, which it can provide. That can be obtained from this compensator. Now I will, okay, now you tell me. So there are many ways. So obviously the one way which we discussed is we will find the corner frequencies. We will find the corner frequencies and we will see what is the frequency at which the phase is maximum. That's omega m, which is given by under root of omega 1 and omega 2. And then we'll directly take the angle and we're done. But there is this formula, sine of phi m, which directly calculates. That is 1 minus alpha divided by 1 plus alpha. So if we are able to find this alpha, then we are done. Okay, then we are done. Okay, now see what is this transfer function? What is the general transfer function of lag compensator? So we wrote that in the beginning. So let me write that. Of a lead compensator, sorry. So we will write the transfer function of a lead compensator, which is GC of S is equal to 1 plus ts divided by 1 plus alpha ts, where alpha is less than 1. Where this alpha is less than 1. Sorry, yeah. Okay. So this is the transfer function of a lead compensator, general transfer function. So somehow, if we are able to find this alpha from our given transfer function, then we are done. We can find phi m easily. Okay. So what is our transfer function? So our transfer function is GC. I'll directly write S as j omega. So 1 plus 0.12 j omega divided by 1 plus 0.04 j omega. This is the transfer function. Now let's compare. So S is j omega here. So if we put S j omega. So what is T? Directly I can write my T is 0.12. If you compare. And what is alpha T? Alpha T is 0.04. But you know T is 0.12. My alpha is 0.04 by 0.12. So it means this and this goes. My alpha comes out to be 1/3. So I got my alpha as 1/3. I'm done. I can directly apply the formula. I can directly apply the formula. So you can directly apply the formula. So I apply the formula. The formula is sine of phi m 1 minus alpha divided by 1 plus alpha. 1 minus 1 over 3 divided by 1 plus 1 over 3. Somebody has solved it. A is 1 by 3. What is the answer you got? You have written 30. Yes. So we'll finally get phi m is equal to sine inverse of 0.5, which is equal to 30 degrees. That's it. Okay, so basically whatever questions that we have solved, you can solve them in this manner as well. So basically what you have to do, just find alpha, and then directly you can apply formula. That is sine of m is, that's the maximum phase shift that this can provide, is given by this formula. Okay, now one more question. So one more question is GC of S is equal to S plus 2, S plus 1. So this is the question which we started with, a similar question we started with, but do it in this fashion. So that this compensator would provide a maximum phase shift off. So basically we have to find the maximum phase shift provided by this compensator. Okay, so you have to basically identify first which type of compensator it is, and then accordingly use the formula. Tell me. Okay, I'll not solve it. You will tell me what is the answer. So find phi m, but before that, tell me which compensator it would be by looking at the poles and zeros.
Lead compensator.
How it is lead compensator? Can you tell me? So in a lead compensator, the pole which is near to origin, pole or zero. In a lead compensator, if you draw the pole zero map of a lead compensator, zero is closer to the origin, but in case of a lag compensator, pole is closer to the origin. Okay, so this is how, otherwise everything remains the same. The transfer function, it remains the same. Just alpha and beta. Alpha will actually vary. Alpha will be less than 1 for a lead compensator. Alpha will be greater than 1, which sometimes people call it beta, which is 1 by alpha. That will be greater than 1. Okay. So now tell me, is it a lead compensator or a lag compensator? So let's write the transfer function. See, GC of S is equal to S plus 2 divided by S plus 1. So the transfer function, yes, it's a lag compensator. See, this is actually the trick which normally where actually you may do the mistakes. So this GC of S, we need to find it in time constant form. So if you find it in time constant form, we'll take 2 common. It will be 1 plus S by 2 divided by nothing, 1 plus S. So what is the 0 here? Corner frequencies basically. Corner frequencies are 2 and 1. So 0 is, so we have a 0. 0 is minus 2, and pole is minus 1. Right? So 2 corner frequencies. So you can solve it question like that, which like the way we did, we were doing it. So right, so we can directly write it's a lag compensator. So when it's a lag compensator, then tell me find the maximum lag compensator. Now the question is, would provide a maximum phase shift of, like what is the maximum phase shift it will provide? Okay, and what is the transfer function of a lag compensator? I'll write it for you. Gc of s, that is equal to 1 plus ts divided by 1 plus beta ts, where beta is greater than 1 and beta is 1 by alpha. And you can directly apply the formula. Formula is, so if you write beta, then your formula directly comes the same way as alpha. Sine inverse of 1 minus beta divided by 1 plus beta. So if you compare, wait. Sorry. Yeah. So if you compare this transfer function, so what is the value of beta t? Beta t you will get as 1, because in the denominator, you see beta t, there is 1 into s. So beta t is 1, right? So, and t is 1 by 2. T is 1 by 2, that is 0.5. It implies my beta is 1 by 1.2, 1 by 0.5, which is 2. So I got it. So my phi m will be sine inverse of 1 minus beta into 1 plus beta. Yeah, Piyush did it. Piyush has solved it correctly. So 1 minus 2 divided by 1 plus 2, which will be equal to sine inverse of minus 1 by 3, which is equal to minus 19.47 degrees. So these are actually the type of questions that you will encounter in this lead lag compensator. So basically, you will be given a transfer function, and then maybe you will be asked find the transfer function of the compensated system, or the same question which we did before, where you were given, like I'm not talking about the assignment. The assignment is very easy. What you have to do, write on paper the transfer function in terms of alpha and beta of the lead and lag compensator. Okay, and then just compare. And your assignment questions will be done in 10 minutes. You just have to remember, see, there are questions like where you have to find the maximum lead, or basically some theoretical questions as well. So, but very simple questions. So what I'm talking about in general is, I'm talking about with respect to your final exam. So in your final exam, you cannot expect that your questions will be solely based on one single topic. For example, you cannot expect this Ladley compensator will be asked like this. It will never be. So because there is a limited question, there are limited questions in your final paper, and limited time, and the examiner has to test all the concepts which you have learned in these 12 weeks. So it is not possible that the examiner can do that if he starts asking individual questions, right? Because there is time limitation as well. I think there is 3 hours. So basically, he may uh, like uh, add with these questions the questions from your second chapter, which is actually feedback, negative feedback, and you might have questions like that. And he might also see basically what you are doing when you are adding a zero to a transfer function. What are you doing when you are adding a pole to transfer function? What are you doing? whether your zero is dominant, whether your pole is dominant. That is what these lag and lead compensators are all about. Because eventually, if you see, basically whatever is the original transfer function, you are making an addition to that transfer function, because you will always connect this compensator, these compensators in forward path. So there will be net change in the transfer function. So basically, what is happening? You are actually either adding a pole to the transfer function or adding a zero to the transfer function. So adding a zero to the transfer function improves its transient characteristics. So it improves its steady. It improves its. If you see in a root locus, when you add a zero to the transfer function, the root locus shifts towards left. So relative stability is improved, right? So it means the addition of zeros to the open loop transfer function, it increases the system's relative stability. At the same time, the addition of poles to the open loop transfer function has the effect of shifting the root locus to the right. And when the root locus is shifted to right, it lowers the system stability. That's what I said in the beginning, that this lag and lead compensators, they're basically used to improve transient response as well as the steady state response. So your lead compensator, it improves the transient response, and your lag compensator, it actually improves the steady state response. That's what I had started with in the beginning, that how it does, because the steady state error has some formula. So then how we can actually, using this lead and lag compensator, ensure that my transient characteristics as well as my steady state characteristics are improved, right? So that's why I was talking about the design. That comes under design part. So I have taken another course in the last semester which was about control engineering. So the lectures of that course are on my YouTube channel, so where you find these lectures as well. So there we had 3 lectures, 3 weeks for control design. One was for P controller, I control, like PID controller design. Other one was for this compensator design using root locus. And then the next lecture was the compensator design using gain margin and phase margin, using frequency response analysis. All right, so that's what I'm saying. But that's not the part of this course. That's beyond the level of this course. But again, in your case, it's very simple. Like, you just have to remember what is this lead lag compensator, how you can draw the transfer function of these lead lag compensators, draw the Bode plot, draw the Nyquist plot. You should be able to understand how you find the angles and where will that maximum angle be, what is the frequency. That's it. That's all. That's all that will be asked in your exam, in your assignment. That's all which is actually asked in your assignment. But yeah, again, talking about your final exams, that will be very tricky because that will mix up concepts. That will mix up concepts. Not only here. For example, the examiner will never ask a question of closed loop feedback or a steady state error simply. He will mix up. He will make a block diagram, and then he will check your concepts of feedback, and then stability, and very importantly, bounded input, bounded output stability. So make sure you revise this course well, because it's very tricky to pass in these exams, because you have some minimum percentage which you have to get, and which is not easy always. Even though this course is a bit simpler, I don't think this will be much harder. But the other course, which was control engineering, again by IIT Madras, that was very difficult. Only few people passed in that course, because that covered everything. That covered controller design, that covered this all basics, and that also touched a bit of controller design in state space. So you have just had only the introduction to state space. Okay, so I'll just stop here. If you have any questions, please ask. And thank you very much. There were a few people who joined throughout these 12 weeks. Shubham is one among them. Thanks, Shubham, for being active. I wish you all the best.
Thank you, sir.
Yes. You are in the third year, right?
Yes, sir.
Okay, okay, great. So you continue working harder, and there is another course that I'm talking about, which is control engineering. I hope your concepts of control are pretty good now, and you are good to go with Gate if you're talking about that, and no need to enroll for other courses. But yeah, if there is some like you have to take that course from your college, then it's better to take that course, which will be useful for you in your Gate as well. Thank you, Marwan, as well, because you have also been consistent from last couple of weeks. Thank you, Piyush. So if you have any questions, please ask. Please ask any questions. So you can ask me general questions as well because we have time. Otherwise, I can just stop the meeting. You can ask any questions. So general questions, not related to the scores. You can ask related to exam. You can ask related to gate preparation or higher studies, etc. Like we can discuss because we have some time.
So can I ask something?
Yeah, yeah, please.
Actually, sir, sorry for not joining the problem solving session since I didn't have enough time
Yeah, yeah, sure.
because
So
of
are
my
you a
other
working
commitment.
professional?
No, sir, I'm also a student in second year.
Which? Oh, just a second. No problem. Which college, Piyush?
It's not a very good college. It's a theatre called Noida
Oh,
International.
that's
It's
fine.
based in Noida.
Where is
Actually,
it?
sir, it's in Greater Noida. Actually, sir, I wanted
Uh-huh.
some suggestion if you can give me. Like, I'm
Uh-huh. Yeah.
actually not related to any electronics branch I'm currently doing because I'm in a computer science engineering. But
Yeah, yeah, yeah. Okay.
and I had to take that for bachelor due to some reasons. But I'm planning to do my higher studies in mainly satellite design in avionics, and I'm trying
Oh,
to
that's
shift
great.
my focus. That's why I'm
Mm-hmm.
doing these all courses. So can you
Mm-hmm.
suggest me like so which courses I should also focus on for mainly the avionics for satellite design part, electronics part of satellite design?
Mm-hmm.
Because
I think you
for
should
initial,
you yeah, great. So control is everywhere. So be it
okay,
electronics, be it mechanical, be it chemical, everywhere you have control, right? So control, you have done a good job. You have enrolled on this course or not enrolling, but you're studying this course. It's a good thing. You should also study some advanced control systems, right? So from state space linear systems theory, because it's very important when you're talking about satellites or any system in general. It's first of all, it's very important to learn its mathematical model, right? So, and that
yes,
mathematical model comes from mathematics, and which actually is taught in control systems or the higher level of control, the advanced control systems, right? So basically, you should learn some linear systems theory course, some at least some courses on linear and nonlinear systems where it's taught how to model them mathematically, right? And at the same time, you should learn some electronic courses, some courses from communication, right? Some courses from microelectronics, nano, etc., etc. So be in touch with them. I think communication would be something of like something very
yes.
important that that have. Yeah.
Yes, I'm actually studying other things too. Like I'm studying that as this course with parallel with this course, I'm studying
Hmm.
Introduction to Aerospace Engineering that was offered by IIT Bombay. Then I'm also studying
Hmm.
from some other place the embedded systems and like
Yeah, embedded systems.
data processing
Yes.
for uh, I mean satellite telemetry and things like that from other platforms like MIT, OCW, or EDX.
Great, great, great. Yeah,
So
that
I
would be
just
a good start. But I don't know. You're in second year. Whether there will be any possibility to change your branch, or you have to be in this computer science branch for now, because this will be a
actually
burden
there
somehow on you.
actually if I had possibility I have changed into electronics branch, but I don't think I will be able to change currently. But I'm going to aim for it in masters.
Okay, okay, yeah, no problem. I have seen many people. I have a friend who is bachelor's in civil engineering. Now he did masters from IIT in physics. because he had interest in physics. And now he'll be
Yes,
pursuing PhD in physics. So started from civil engineering, now doing physics and doing another, again, continuing in physics. So there's no problem at all. So make sure that you do not rush study. I know you will not study it in that detail that uh, will lead to your goal. But yeah, make sure you pursue your masters from a good institute and in a good
yes,
subject. For that, you should at least qualify GATE in that subject. For
yes,
example,
I'm
it will be
planning
very
to.
okay if you pursue your masters in electronics or embedded systems, or for that crack GATE double like EC or instrumentation or GATE physics. There are some exams in physics as well.
Yes, sir.
Just, but I don't think physics will be of your will be important for you because you will be in design part, right? Satellite design, etc.
Yes, sir. Yes, sir.
So I think electronics would be like very important for you to begin with.
Yes, sir. Yes, sir.
And make sure you do one more control course for mathematical modeling and design. Design is very important, right? So, for example, you're sending some satellite and that has to land properly with some proper speed, or I don't know much. Uh,
Yes,
like
yes.
the landing gear has to have proper orientation. So those things will be taught in control, right? Controller design, how we will design your controller such that those things are achieved, right?
Yes, sir.
So,
That's
so,
what
so
that's actually I wanted. If you can give me suggestion, like the next semester, which is going to start about NPTEL, I'm
control
planning to
engineering,
like.
yeah.
Yes,
If your concepts are good as far as this control is concerned, then no problem. You can pursue this course. I will write here on my screen. You
okay, sir.
can pursue
It's
this
it's
course.
for me. It doesn't necessarily have to be from NPTEL. If it's from somewhere else, I can just get the content that's in it.
Yes, yes. Okay. Linear systems theory. It's from NPTEL. It's taught by Professor Ram Krishna Pasumarthy. I think it will run next semester or maybe the other semester. I don't know exactly. Maybe you have to check. So linear systems theory will be a very good course for you. And also check Steve Brunton, and this is one channel, YouTube channel, and Brain Douglas. Check these two YouTube channels. They'll be
Okay, sir.
very useful for learning control concepts, in particular the classical controls. So maybe the videos of Brian will be very useful to you. So
Okay,
do
sir.
that. So check these two YouTube channels, and I think then that will be very very good for you.
Thank you, sir.
Yeah. Okay. Shubham, you want to ask anything? Shubham, are you there?
Sir, now I am in fifth semester.
Okay. Good.
So in our college, the project, the practical, I
Uh-huh.
cannot able to do small projects. Then can I learn the projects from any platform?
You can always learn it from YouTube. For example, if you have interest in control systems, Arduino, microcontrollers, you can search it on YouTube,
Yes,
and there are always some mini projects there, right? So that's one way. And other way is do something with MATLAB, you know. Uh,
yes,
uh, you have ChatGPT, ask ChatGPT to create some project for me and then implement that on MATLAB and actually try to convince yourself, okay, this is actually happening, right? So even if you're using ChatGPT or other AI tools, but if you're learning it well, if you're able to convince yourself, then that's all. That's all is needed. Okay.
yes, sir. Okay, sir.
As of now, focus on your gate if that is your primary objective. So focus on that, and I hope this control course works for you and you score well in that. And rest, I wish you all the best, and I wish all the students of this course all the best uh, for their final exam. It was nice interacting with you for these 12 weeks. Thank you very much for attending. Yeah, thank you once again.
Thank you as well, sir.
Yeah, thank you.
Yes.
Thank you, sir.
Thank you. So I'm ending this.